Okay, so it is a pleasure to introduce Xuhua He from University of Maryland. So he will give a talk about Hecke algebras and p-adic groups. I should also say that I was very lucky to have him as a PhD student. It was quite enjoyable for me, and that was about 10 years ago. And after that, he spent several years in Hong Kong at University of Science and Technology, and more recently moved to Maryland. And in 2 years ago, he was awarded the Morningside gold medal for mathematics. So please give the talk. Yes.
Okay, and just first, thank you for the introduction. And I'd like to say that I think this is a wise decision that actually, when I first entered in MIT, actually I chose you as my advisor. And actually, I learned really quite a lot from you, and I still benefit from this, and you're going to see from the talks. And thanks everyone for showing up in this very early Saturday morning. And I'd like to thank the CDM organizers for inviting me and for allowing me to give the 2 talks. And so I'm going to talk about two of my favorite subjects, arithmetic geometry and representation theory. So it's good to have the 2 talks, so I don't have to pick up one. And the first talk, I'll be just talking about things related to the arithmetic geometry, and in the second one, I'm going to focus on the representation theory. Well, so the 2 talks just linked by one idea or one motive. So here the motive, I mean it literally, just this repeating notes in the music, or some repeating ideas in several of the papers, or some repeating slides in my 2 talks. And well, in the 1957, so Tietz wrote in his papers what nowadays we call the Tietz philosophy. It's just he wants to think about the finite wire groups as a reductive group over F1, the field of one element. And the typical example of the wire group and the reductive group, you can say, is Sn, the symmetric group of the n object. And one way to think about this is that we think about this as the invertible n by n matrices over the field of one element. Well, I should say, I mean, from the definition of the field, F1 does not exist. But nowadays, I mean, the field of one element is actually very powerful, and there is a very amazing theorem behind this. Well, this is not what I'm going to talk about. What I would like to, what I'm really curious is that what happens for the p-adic groups and for the affine wire groups. And well, so based on the Tietz philosophy, we may ask whether or not an affine wire group should be a reductive group over Q1, the one-adic field. And the quick answer to this, I do not know. And I think it's actually probably too early to ask that question. I mean, I think that first we have to have the well-developed field of one-element theory. Then, after that, we can actually seriously develop a theory like this. However, what I want to say is that, in fact, now we do have a good understanding about some close relations between the affine wire groups and the p-adic groups. And so what we're going to talk about is that we're going to talk about some questions related to the conjugacy classes. And we're going to think about this actually in the two directions. We're going to think about the affine wire groups as a degeneration of a p-adic group. And then we're going to say the p-adic groups are the deformation of an affine wire group. And we're going to say how this observation actually helps us to understand many questions. Okay. So now it comes to the motivation for this first talk. So in the first talk, I'm going to focus on the following problems. So first talk, I'm going to focus on the intersection of the Xuhua cell intersects with the conjugacy class. Well, I'm going to talk about many in the affine setting, but the motivation, one of the motivation actually do comes from the finite case. So here, let's say if we start with, excuse me. So if we start with, let's say, a reductive group over algebraic closed field, and thank you. And we pick up the Barrel and the finite wire group. So we have this is the Xuhua decomposition. So each one is called the Xuhua cell. On the other hand, we have the conjugacy classes. For example, we can write the G as a disjoint union of the conjugacy classes. Now we have the two decompositions. We like to say what are the relations between these two. And typical example here, we again back to the GON case. And the wire group is SM. And for the conjugacy classes, we know that we have this Jordan decomposition. So it's just a semi-simple plus unipotent. And well, so this really amazing and still mysterious relationships between the conjugacy classes of the finite wire group and the conjugacy classes of the reductive group discovered by Lustig. So by looking at these intersections. And well, now what happens for the p-adic groups? And there's another motivation that we do care about such question for the p-adic groups. So this actually comes from the Mader's work on the isocrystals. So here now we think about the F, which is the non-Archimedean local field. Or for example, you can think about this as QP or the Laurent series of FQ. And we take the F brave to be this completion of the maximum ramified extension. And then we have this Frobenius. Okay, what is an isocrystal? So this is a linear algebra data. It just consists of the five-dimensional vector space M and a semi-linear bijection. A crystal is just a G-stable lattice in this vector space. And we have the invariants associated to the crystals and isocrystals. So for the isocrystal, we can associate to the Newton slope. And for the crystal, we can associate to the Hodge slope. I'm not going to give you a definition, but I'm just to show you with one example. So here we start with a three-dimensional vector space, and they say the G sends the first, they have the basis E1, E2, E3. G sends the first one to the second one to the third one, and the third one to the epsilon times the first one. So here the epsilon is a uniformizer. And if you write down the matrix and compute the eigenvalue, you know the eigenvalues are all cubic root of this uniformizer. And then we take the evaluation, we get the Newton slope. So this is, in this case, this is, so in this case, this is the 1/3, 1/3, 1/3. And if you compute the Hodge slope, so you see here this is, no, this is epsilon to 0, epsilon to 0, epsilon to 1. So what you get just is 1, 0, 0. And let's compare the Newton slope with the Hodge slope. And then what we can say is that one, two, three, and 1. So this is Newton. And Hodge is 1, 0, 0. So then this one is Hodge. And you may say here that, okay, you may say here that they have the same ending point, and Hodge is above the Newton. And in other words, so we say we just have a sequence of the positive numbers, and there is a so-called Dom's order. And so here, this picture just says that in the Dom's order, the Hodge slope is larger than or equal to the Newton slope. And so this is just one example. But what Mazur showed in 1973 is that this is actually true in general. So whenever you have the isocrystal and the crystal, then the Newton slope then the Hodge slope of the crystal is always larger than or equal to the Newton slope of the isocrystal. And the Cartwright and the Rappaport prove the converse after 30 years. They say that if you are given an isocrystal and given a sequence of the positive integers such that this sequence is larger than or equal to the Newton slope, then we are able to find a crystal of this with this given sequence of the numbers. And now we would like to reformulate this in a more group-theoretic language. So here, the group G is just a GOM, because we just consider about the fine-dimensional vector space with no additional structures. And we have this K is that this is the maximal compact in maximal compact in G. So what is isocrystal? We look at the vector space together with the semi-linear bijection. They just say that we just give them a Frobenius twisted conjugacy class of an element in this group. And what is a crystal? Crystal corresponds to the lattice. So this just corresponds to the K times K double coset. And so what we have seen above, this theorem, is what we just refer to as a Mazur's inequality. This just basically says that this K mu K intersection with this sigma conjugate class is non-empty if and only if the Newton slope is less than or equal to the Hodge slope. Okay, now we may just, so this is just for the GOM, and we would like to ask this question for arbitrary reductive group over the p-adic numbers. And this also has applications in the number theory, and we are going to come back to that point later. So here the general setting is that we start with a group over a p-adic field, and we put a Frobenius morphism. And so here we want to choose a Iwahari subgroup. So the Iwahari is, and think about the Iwahari as the inverse image of the standard Borers inside this maximal compact. And then we have this associated Iwahari Wire group. Well, let's come back to this GON case. Then this Iwahari subgroup, this is just content of the Sn, as we have seen before. But it also has this lattice part. So this is a Zn, and we know that the Sn acts on this Zn, this form the semi-direct product. And then we have this so-called the Iwahari-Buchard decomposition. So we can write this G over F brave as a disjoint unions of the double coset of the Iwahari. And okay, so I'd like to point out that this Iwahari wire group, this is what we being a quasi-Coxeter group. So this is a Coxeter group, and semi-direct product with another group consists of the automorphisms. And well, what's important is that it has a natural Buchard order, and we're going to say that this actually plays a role in our later discussion, and also the length functions. And the length function is actually be very important for both of these talks. What you can see here is that we do see this in a geometrical way. For example, the dimension is equal to the length. And taking the closure, we're going to say this just involves the Buchard order. And what we can do is that you can do the general case. Instead of thinking about the Iwahari, we can think about the Parahoric. And for each Parahoric, we have the finite wire group associated to it. And then we have the similar decomposition. And a very important special case is that when we say the K is special, then in this case, this double coset are in the natural bijection with what we call the dominant co-weight. So we have this decomposition, the K mu K decomposition. And we have seen this already appears when we talk about the Mazur's inequality. Okay, the other thing is about the conjugacy class. So here, for the applications to the Shimura variety, we would like to consider about the Frobenius twisted conjugacy classes. And so we denote this by BG. And Cartwright in 1985 and 1997 gave classifications of this BG. So this BG is actually given by the two invariant, is determined by the two invariants. So the first one just basically the coset. And the second one, so this is the Newton slope. And we would like to give a more explicit way to understand this. So the way that I found, and I think this actually also shows some relations between the affine wire groups and the p-adic groups, is that we can actually think about the sigma conjugacy classes for the Iwahari wire groups as well. Then we have a natural map from this set of conjugacy classes to a set of conjugacy classes for G. And so the non-trivial, well, we have this well-defined map to make this diagram commute. The non-trivial fact is that this map is surjective. Or in other words, any sigma conjugacy class can be represented by some element from the Iwahari wire group. And still, so you may not be very satisfied with this picture because this map is not injective. Well, but we do have the way to fix this problem. And by introducing some special conjugacy classes of the affine wire group. So here, the idea is that we say an element is straight if we take the higher power, compute the length is always equal to that power times the length of this element. And these are very special conjugacy classes. And if we just take into those special conjugacy classes, then we have this is a natural bijection between the set of these special conjugacy classes with the conjugacy classes in G. So here you may ask what happens for this double line. So it looks like the GIT quotient. And well, so I really did this on purpose. And then later on, we're going to say we are able to introduce a partial order to make this a topological space so that it will be compatible with the partial orders on this side. Well, but so far, so we just have to say, OK, this is just a set theoretic statement. And well, the idea behind it, how do we actually get this and these pictures? And the idea behind this is that we want to consider the conjugations on this decomposition. We have this decomposition into this double coset, but still we want to think about the conjugation on it. And well, so there is a very simple but important observation which comes from the Bohr lemma, says that if you take into account of this conjugation, and let's say we also have this simple reflections in G, we want to say how it changes. There are actually two situations. One is that if we preserve the length, okay, then we have the simple formula for this. This sigma conjugation on this IWI is the same as the sigma conjugations on this the ISW sigma SI. That's like the Euro conjugation actions on the Affine group. But the second case is actually more interesting. When the length becomes smaller, then then besides this one, we also have another one which goes outside of this conjugacy class. And well, what this actually indicates, so this indicates that in order to understand about the sigma conjugacy classes, what we need is that we not only need the information on the sigma conjugacy classes of the Iwahawi wide group, but also we need to keep track of the length of this element as well. So in some sense, when we say that we think about the Affine wide groups as the p-adic group over as a one-adic group, we do mean that we really want to keep track of not only the information on the Affine wide group, but also we want to keep track of the length functions as well. Well, what can we say about the length function? Well, so this actually back to the 1993 of the paper by Geck and Pfeiffer. Well, they considered the following questions for the finite wide group, and the motivation actually comes from the Hecke algebra, which we'll come back in the second talk. So well, the final result, so this is 2012 joint with Nier, and then 2014, we actually did this for the Affine case, is that if the W is the finite Coxeter group or the Iwahawi wide group, and if you have the diagonal automorphism, if you fix the conjugacy class, then if you start with any element, you can find the sequence of simple reflections such that the length always goes down, eventually reach a minimum one. And also we have the nice relations between the minimum length elements. And the upshot of this is that now we finally have the reduction method, which allows us to understand about the sigma conjugacy classes, and more importantly, to understand about the intersection of the IWI intersection with the sigma conjugacy classes as well. So this is a, let's see, this is a Bourgeois cell intersection with the conjugacy class. And well, why do we really care about this IWI intersection with B? You have already seen that it appears in the work of the Maser and Cartwright-Rappaport. As in fact, what you have is that, so I would say such intersection actually, well, I put this for the more general case, case of Parahoric. So why we actually care about this? Because it's actually one reason. Well, first of all, this is a very interesting group theoretical question. And second, it has important applications towards the Shimura varieties. Okay, so let me first put this one there. So this is just a disjoint unions of the certain double coset, and we'll come back to that point later. So just now, right now, just only we need to remember this is a certain union. And well, the good thing is that we actually have a group theoretical models for the special fibers of the Shimura varieties. And so this side is what happens for the Shimura variety. On the Shimura variety, we have the two important stratifications. Cartwright-Rappaport stratification, identified by KR, and the Newton stratification. So this is actually indexed by the certain elements in the double coset, and this is actually indexed by the sigma conjugacy classes. And the several fundamental questions are, first, whether or not they are non-empty, and the second, whether if they are non-empty, are their intersection non-empty? And also, about if they are non-empty, what are their dimensions? And if they are non-empty, what about the closure? And this question has been studied by many people. For example, Ekta, Cartwright, Rappaport, Chai, Keesing, and many others. And I'll say here we look at on the group theoretical side. So this MK, I think about this as a group theoretical model. What is a group theoretical models for the Cartwright-Rappaport? This double coset. For the Newton is that these unions of the double coset intersect with the sigma conjugacy class. And the dimension, okay, so I'll come back to this dimension later, the dimension of K. And taking the closure is just taking the closure on the other side. Well, if you actually think about this, is that, well, in fact, so here we actually taking the closures in the p-adic group. They are infinite dimensional. But, so the key observation is that if we take this intersection, so this is stable under the white multiplications of a very small open compact. And so we just introduce this K dimension, which means that we just kind of quotient this by K. Although quotient this by K doesn't make sense because this is not stable on the K. So just quoting out a very small open compact, and we look at the difference of this dimension. And taking the closure is defined in a similar way by looking at the G of F with quotient by IN. So these two actually now make sense. And well, so what I'm going to do next is I'm going to discuss about what happens on this group theoretical side. And in the end, we'll come back to this Shimura side. Well, what can we say about the intersection? So here, I just focus on the intersection of the IWI with B. Because if you think about the Parahoric, let's say the KWK, but KWK is always the unions of the double coset of the Iwahari. So basically, if you understand what happens for this, then we actually understand what happens for the other Parahoric as well. Okay, now So here we have this theorem, which actually gives a formula for this dimension. So if you pick up an element in the you have a wire group, pick up a sigma conjugacy class, then taking this intersection, this is the same as a degrees of certain polynomial. This is a class polynomials of the Affine Hecke algebra. And so we actually have we actually do have an algorithm for this. It's a complicated algorithm, but in practice, we're able to compute this in the small ranks. And also, I should say what's more important is that this actually gives a more algebraic way to understand this geometric object. Oh, I should also mention that this is not only about the dimension, but also tells you when it is non-empty. So here we say that the empty one has a dimension minus infinity. And also the degree 0 has a dimension minus infinity. So this one is non-empty if and only if the class polynomial is non-zero. Okay, so actually for the people in studying the Shimura variety, and the group-theoretic model they often use is not this intersection, but the affine elusive variety. So here the affine elusive variety is subvarieties of the affine flag or affine Grassmannian given by this condition. G inverse B sigma G is contained in this the KWK. So here we can say after you actually do this conjugation, you actually get the sigma conjugacy class of B. So this one is non-empty if and only if the intersection we discussed is non-empty. And also this one is finite dimensional. However, I feel that in some sense, this intersection behaves better than the affine elusive varieties. And one reason is the following one, that we have the relation between the dimension of both. So the difference is that this is some number, this is a Newton point, this is just a sum of the positive roots. And well, what is the meaning of this? This is actually the dimensions of the central leaves of the Shimura varieties. So in some sense, this actually captures more information about the Shimura variety than this one. Okay, so we have this formula, the dimension equal to a degree. But another question is that, what can we say explicitly about this side or about this side? Well, so here we have some more explicit descriptions. Well, first, let's say we consider a special maximum Parahoric. Then now we have the complete answer when this intersection is non-empty. Well, this intersection is non-empty if and only if the major inequality is satisfied. So this is a generalizations of the work of the Mazur and Cartwright and Rappaport. And so in fact, this, so in the 2003 paper, the Cartwright and Rappaport proved the converse for GLN, and then they conjecture this is actually true in general for arbitrary group. So now we actually finally have this. And the second is that not only we know when the intersection is non-empty, but we actually have an explicit formula for the dimension. And this is actually conjectured by Rappaport. And okay, so this is what I want to say about the special Parahoric. Now, if you just think about the Iwahari or arbitrary Parahoric, well, the very important case is that the sigma conjugacy class is basic. And well, the basic means that the Newton point is central, that the evaluation with any finite root is 0. And in this case, we have a complete answer for the intersection, for the non-emptiness pattern of this intersection. The IWI intersection with B is non-empty. Oh, I forgot the type. It's if and only if. If and only if there is no Levy obstruction. And this is actually conjectured by Gauss, Hens, Cartwright, and Riemann, and actually proved in the joint work with Goetz and Lie. And now let's come back to the dimension. So for arbitrary W and for arbitrary B, so we introduce this virtual dimension. So this virtual dimension gives an upper bound. And well, how good this upper bound is? So in fact, for the basic B, and in many, many cases, in fact, this is indeed the correct bound. So this is actually conjectured by the Gauss, Hens, Cartwright, and Riemann, and then we established this. Okay, so I haven't explained the Schwanken-wide chamber. So roughly speaking, the Schwanken-wide chamber is that you consider about the lowest two-sided cells in the Affine-wide group. So this really covers most of the cases for the most of the elements in the Affine-wide group. Okay, and any questions? Okay, so now we actually come to this is the double line. This is the double line, and I want to introduce a partial orders on this. And the motivation to introduce this partial order because I will want to understand some questions on the geometry. So this actually gives the motivation to introduce this partial order. So here we say that if we are given the two straight conjugacy classes, you see one is less than the other if we are able to find the minimum length element and we are able to compare them in the Euler-Buchau order. And well, we have seen this diagram before without these partial orders. But now we say, okay, so this diagram works perfectly well with the partial order. So here, this order is the order induced by the Buchau orders. And this one is coming from taking the closure relation. Take the closure of one sigma conjugacy class. This is the unions of the others, just this closure relation. And on this one, so this is the Endowment's orders on the Newton slope. And we say that these three are actually compatible. And I would say the proof of this is actually kind of interesting, is that in fact it actually involves both the combinatorics and the geometry. You can say here, even for this, so this direction, this actually relates to the Grothendieck conjecture. This is a geometric statement. And this one, you can say, in fact, this one is just a purely combinatorial statement. But in order to prove this, in fact, we actually do use a geometry. We use some parity theorems. So this actually is, in fact, a combination of the many different methods in order to finally get this one. Oh, okay. So now, so far, this is just basically the group theoretical question. And now we are aiming to say something which has a relation to the Shimura variety. So remember in the beginning, so we set this group theoretical models for the Shimura variety. And so this is a certain unions of the double coset. Now, what is this index set? And okay, let's come to this index set. So this index set actually, so related to a dominant co-weight. And in application, so this mu actually comes from the Shimura data. And this admissible set, what is admissible set? So we have this mu. So the mu will give some translation element in the Affine group. And this admissible set says that, okay, we just pick up all those elements in the Affine group that is less than or equal to some translation associated to mu. And then if you have this, so this is actually for the, this is the index set associated to the Xuhua He, and the index set associated to the Parahoric is that we look at its image in this double coset. And another important thing is that, so this is actually index set for the Affine group elements. And we have another index set for the sigma conjugacy classes. This is just the subset of the sigma conjugacy class where the major inequality is satisfied. And I should say, well, there is a long history which actually leads to the definitions of this admissible set as well. So this actually relates to the so-called local models of the Shimura varieties. And so what are the relations between this index, this subset of the double of the Xuhua He group or the double coset and the subset of the sigma conjugacy classes? And so this is actually, we finally have this is a nice correspondence between these two subsets. So here, the result is as follows. We consider this union. Then we look at those sigma conjugacy classes which actually intersect with these unions of the K double coset. And the answer is that this intersection is non-empty if and only if the sigma conjugacy class is contained in this is the BG mu. In other words, for those sigma conjugacy classes that has application to a Shimura variety are just exactly those coming from the Mazur's inequalities. And so this is actually, in fact, conjectured by Cartwright and Rappaport. And it's actually proved by Winter-Berger for the quasi-split groups. And finally, we actually know this is actually true for arbitrary p-adic groups. And well, once we know this is non-empty, so we may take its closure and ask, what can we say about its closure? And so here so this is actually the group-theoretic analog of the Grothendieck conjecture. And says, okay, so if you have this group-theoretic model intersects with the sigma conjugacy class, taking the closure, and we say which sigma conjugacy class actually intersects with this. And the answer is that this holds if and only if the Newton slope of this sigma conjugacy class B prime is less than or equal to the Newton slope of the sigma conjugacy class of B in the dominance order. And okay, finally, we have some, let me discuss about some applications to the Shimura varieties. And well, I have to say that we actually do have the several axioms that need to be verified. And part of the reason is that we want to consider about the general Shimura varieties, and we do not want to put any conditions on that. But then in several cases, what we have is that we actually do require the integral models, and in several cases, the integral model has not been constructed yet. So this is the reason that instead of listing all those conditions, we just put those as axioms. Well, and first we are able to say under these axioms, we know that the Cartwright-Rappaport strata is non-empty if and only if this W comes from this admissible set. So this is the natural region as we expected. And the second, the Newton strata is non-empty if and only if the sigma conjugacy class comes from this set, the BG mu. So in other words, the sigma conjugacy class satisfies the Mazur's inequality. So this one is in fact actually conjectured by Rappaport and also by Manin. And now we can talk about the closure relations between the Newton stratas. We say that the closure of one Newton strata intersects with another Newton strata if and only if we have these dominant orders between the Newton slope. And this is the Cartwright conjecture. This is a Grothendieck conjecture. And so, and in fact, for the Shimura varieties with the arbitrary Parahoric level structure, in addition to the Cartwright-Rappaport strata, we have another refinement. And so this is Cartwright-Rappaport stratification. And so this actually interpolates the Cartwright-Rappaport strata for the Iwahari case and the Ickta-Ott strata in the hyperspecial case. And so Rappaport says that, okay, then since it is the interplace of these two, and we should interplay the names. So this is Ickta-Ott and Cartwright-Rappaport. And so in fact, another thing is that I should say that the definitions of this, the EKOR strata, is actually, so the group-theoretic analog of this actually was actually in the Lusik's papers, the parabolic capital sheaves, and we just put his settings to this case. And this, in fact, it actually looks good. And so I should say that one of the reasons that we want to introduce this refinement is that in some sense, the Cartwright-Rappaport strata is not good enough if we want to consider the Parahoric level structure. For example, if you think about the hyperspecial case, there is only one Cartwright-Rappaport strata, and which is not very useful. However, for this refinement, then I think this, in some sense, this is actually good enough. For example, this is actually good enough for the purpose of the Newton strata. For each given Newton strata, we can find a echo strata which entirely contained in the Newton strata. And such thing does not happen for the Cartwright-Rappaport strata in general. Okay, so I will stop here and thank you.